Problem 2, using a linear inequality. Entertainment. The map shows the number of tickets needed for small or large rides at the fair. You do not want to spend more than $15 on tickets. How many small or large rides can you ride? Well, note the image. Large rides cost 5 tickets, small rides 3 tickets, and we have a ticket booth. Tickets are 25 cents. You can buy 60 tickets with $15. So, to begin to relate the quantities in this problem, we can relate the number of tickets for small rides plus the number of tickets for large rides is less than or equal to 60. And define some variables. We'll let x equal the number of small rides and y the number of large rides. So we'll write 3x plus 5y is less than or equal to 60. Continuing on, step 1, find the intercepts of the boundary line and use the intercepts to graph the boundary line. Up until this point, our inequalities have been given to us in slope-intercept form, but now that this one is not, it might be easier to find the x and y intercept to graph the inequality. So when y equals 0, substituting 0 into the equation 3x plus 5 times 0 equals 60, solving for x, we find that x equals 20. So our x-intercept will be 20, 0. When x equals 0, well, 3 times 0 plus 5y equals 60. Solving, we find that y equals 12. So our y-intercept will be the point 0, 12. We can use these to graph the line that connects the intercepts, 20, 0 and 0, 12. Since the inequality is less than or equal to, we need a solid boundary line because the points on the line will be solutions in this case. Step 2, the region above the boundary line represents the combinations of rides that require more than 60 tickets. Now we only have 60 tickets, so that's not the region we're going to shade. You purchased a finite number, so not infinite. That was 60 tickets, so you will not be able to go on an infinite number of rides. Shade the region below the boundary line. The number of small rides x and the number of large rides y are whole numbers. In math, such a situation is called discrete. All points with whole number coordinates in the shaded region represent possible combinations of small and large rides. So we can see a blown up image here with points shaded representing whole numbers or numbers of rides that you could go on with 60 tickets. The thing to note here is you couldn't go on 3.5 rides. That doesn't make sense in this situation. So only whole numbers are reasonable solutions. Your turn, part A. Suppose that you decide to spend no more than $30 for tickets. What are the possible combinations of small and large rides that you can ride now? Use a graph to find your answer. And part B, a reasoning item. Why did the graph of the solution in problem 2 only include quadrant 1?